on here are things at the very end of the program, so I'll get to them later. The program began 6 years ago, almost today, with this blurb in the form, February 22nd, 2006, announcing the fact that NDSU was going to be working with MIT on some program that would result in the creation of spray-on computers. I'm not here today to show you a spray-on computer. I'm explaining what we actually did instead. Okay, but that's how it started. So we worked with MIT for quite a while. For the first couple of years, in 2008, you recognize the building on the top. The one on the right is at MIT, the lab that I frequently visited there is down in the basement of that building. You have to go through the Lego room, and then another lab when you get to this lab called Center for Bits and Atoms. All right, now the impetus for this program and many others around the world is basically this idea that we should be able to make things using a lot of very small, cheap, simple parts. And I think what got people thinking that way was the integrated circuits kept getting smaller and smaller, so started imagining making processors the size of a matchstick head. And they looked at what we'd learned about biology and DNA, and they started imagining maybe we could make some kind of biological parts. And all the people who were not part of electronics before suddenly could see how they could get involved, being biologists and chemists and whatnot. And so everybody had their way of somehow doing this. And different ideas, and they're still pursuing them now. I've listed here programmable materials, smart matter, little robots that run around, very tiny ones you can't see, and computers. My focus is on computers. Okay. When it comes to computers, there's a lot of ways to think about computers consisting of many small, inexpensive parts. And one of the inspirations that people turn to is cellular automata. I don't have time to go into what that is. And neural nets, wireless sensor networks, these are all common. Amorphous computers, okay, there's something you maybe didn't hear about, but basically it's like a wireless sensor net where the nodes are so close together that communication is very local. Okay, so an example of that is actually on the right here. This is called a push-pin computer. Every one of those little dots that you can hardly see is actually a little device about this high that you push into the back plane, which supplies power. And they're designed sort of like lamp posts. There's little lights on top, and they shine down on neighboring pixels. And so that these little dots communicate with each other optically. So it's amorphous in a sense, but it's really a very tightly packed sensor system. But every one of these little pins carries a computer. And so this letter A that you might make out was drawn without any central control. It just sent in information, and these processors all communicated with each other and drew out the letter A. So that's kind of the amorphous computing idea. It led to another program called paintable computers, and conformal computing was a derivative of that. So there's been a series of programs related to this effort to make computers out of many small parts. Okay? Keep that in mind, because that's kind of the theme through this, that what can we do if we had a whole bunch of things that were all the same, or nearly so, and they were cheap and small. But one thing that changed for me was this idea of being amorphous is difficult, because now things have to communicate in some wireless way. They also need power somehow. Those are tough problems, and you really have to ask, do the applications that are out there require that? Many don't. There are many applications where you don't need to actually have them physically separate. Okay, so conformal computing, that's what I'm going to be talking about today. These are the things I'm going to go through. Each one of them is associated with an artifact of some kind. So we started out making wallpaper computers. Okay, and we talked about painting computers, so why not use wallpaper if you don't have paint, right? So it's kind of the same idea. But what's different, and you know, when you think about wallpaper, is it's already a thing. that has some kind of spatial dimension to it. That allows us to attach wires to things, which takes care of two big problems, supplying power and communication. So if we go with wallpaper instead of paint, we can do a lot of the same things you would do with paint, but it's a lot easier to implement. Okay, so that's kind of the track then that we pursued, was this idea of a wallpaper computer. But what should a wallpaper computer be? Well, it's what we made it to be, all right? And started out with the idea it should be very thin, ideally flexible, and you should be able to make it as big as a wall, all right? So we started out with this little prototype put together in the first couple months of the program. I have a picture of it here. It's a display on one side, but if you look on the back, here's the display side, and over here is 4 processors. These processors control a subset of this set of display pixels, right? And it forms a tile. A tile suggests a repeatable pattern, right? It's a 2x2 array of tiles. So if we designed our tiles right, we should be able to make an 8x8 array, right? And what we did is made an 8x8 array, right? Same tile design. Now the point is you should be able to keep extending this and make it bigger and bigger. We started running into some real issues, however. The companies that fabricated these green boards for us wanted to charge more money because we had so many holes in the board. And we started thinking about the machines that you run these things through. They only have a certain width. You know, so how do you make something really big if you have these kind of constraints? So we had to start thinking again. And came up with this idea. Let's make it out of strips. We could even design machines that output these strips, and we can roll them up on big reels. And if we have some way of putting the strips together, we could make large area displays. Still have other issues though, like how to get power to it and so forth. But we decided we'd find out what does it take to do this. So first question though is how do you get the strips together? And came up with this idea. If we could make the strips thin enough, we could actually stack them, just like the siding on a house. That's what you see here, or shingles. But how do you connect from one to the other? Well, the idea we came up with, I don't know what slides I have next, this isn't quite interesting. Well, first of all, to make the strip flexible, it can't have a lot of layers of metal. So we had to figure out how to do it in just 2 layers of metal. That's the minimum we get by with. You can get materials that are just like 32mm film that we could actually build circuits out of. Came up with this idea. Chris was a big part of that. We tested it early on. We thought that if we could have a hole on one strip and then a little pad below on the strip below it, we filled that hole with solder, we could melt the solder and gravity would pull it down and it would touch the pad and form a joint. And we tested the idea and it worked pretty good. So that's the idea. We make little teeny holes, they're very small, and little teeny pads, and we can make connections between the strips. And that could be done in a mass-produced way. Just heat the whole area and it all join up. So we actually put together then another version of this 8x8, but this time we used these little strips and then soldered them together to make this complete device. Now, I wanted this to be flexible. Our first prototype is pretty brittle. It's not designed to be bent. But you could actually, in addition to the solder that holds it together, you could put glue, and make it one solid piece that you can then flex. Okay? So what I've just described, this is counterintuitive. I have to push it down to make it go. These are not all the wallpaper computer prototypes that we made. It takes us up to here, right? There's one more. This one took 4 years. I'll talk about it. But while we had this, we wanted to start playing with it for a while, seeing what kinds of things you can do with it. So I'm going to spend a little time talking about some of the things we did with this that give us some idea what kind of applications you might employ these things for and what kind of issues you run into. Okay? So here's some things that we did with it. We've got 6 of them there. In the beginning, I'd say application services. We had to develop software that would run on a distributed system like this. That 8 by 8, that's 64 processors. Somehow those 64 processors need to work together. So we developed an operating system that at first was used for cellular automata emulation. Cellular automata is often abbreviated CA. So we called the operating system chaos because it brings order backwards. Anyway, so application services, that's the software, and I'd like to have a lot of slides on software, but software is so one of the intangible things. It takes a lot of time to develop. I'm just going to say a few things about what the software does. One thing it does is get the code into those 64 processors somehow. Second thing is it handles all the display refreshing. That turns on the LEDs. We have to have the processors communicate with each other somehow. They pass messages back and forth. And then this thread management, if you know a lot about operating systems, you might realize there's generally a lot of activity going on concurrently, and a good way to handle that is with this notion of a thread. So we built that all into this operating system that we developed. So here's a quick look at some of those issues. How do you get code into 64 processors? Well, we developed what we think of as like a virus. You program one processor, this one here, and then it makes a copy of itself in the next one, and then passes it along. So all we had to do was provide a mechanism for doing that, which is tricky, but we worked it out. Okay, displaying the LEDs. The thing is, each processor controls 48 LEDs. And these processors are little teeny processors. They don't have 48 pins on them. So how do you control 48 LEDs with a processor that has very few pins? Plus you need pins for loading code, and talking to other processors, for power, resetting, and so forth. So there's this little trick called Charlie plexing, where with 9 pins you can turn on and off up to 72 LEDs. So that's what this is showing, is how we do Charlie plexing. So it's just a clever little way to turn on LEDs, but effectively you just have one on at a time. That's Charlie plexing. So I mention it now because we use a different scheme later, and I'll explain why. One of the reasons I'm going into these in a little bit of detail is just to give you a feel for the issues that come up when you're writing this software. It isn't a matter of sitting down one day and writing it all up. It's all kinds of questions that come up. One of the questions we had was the processor, which I'm showing here, one processor, it has a one wire connecting it to the next processor. And I have to use that one wire, because I need the rest of the wires for this LEDs and stuff, to talk to that processor. But what if that processor wants to talk to me? Well, it's a bad thing in electronics if two things drive the same wire. So we had to think of some solution. One solution was to put a big resistor in there so if they ever tried to do that, they wouldn't damage each other. But the other thing we did is made up this rule where you can only initiate conversation on one end of the pipe. Okay, so you never have the issue where they both talk at the same time. But it does mean that you have to wait for the other guy, if you ever want to talk to him, to ask if you'd like to speak. That's not so good. So if we worked it out so there's loops in here. So like, let's say that this processor wants to talk to that one, but the wire between them is under the control of this white processor. So the way you talk to it then is this roundabout path. Because you can initiate this conversation, this processor can initiate that one can initiate that one. Okay. So just a little scheme we came up with, and then we had to live with it, that allowed us to get by with a single wire. Now in our new version we have 2 wires. You can guess why. All right, so that's just a little dipping in of it so we get a feel for what's involved in writing software. That's just to get the conversation started. Then you have to actually talk. Now another issue is each one of these processors has its own internal clock. They're not the same speeds exactly. So there's a lot of questions now about synchronizing between the two, and we came with a couple different schemes for handling that as well. But that took a lot of thought. Okay, so now, once we have this operating system in there, we'd like to do some applications. One application is the idea of Pong game. And I don't know how many know about Pong. Pretty good. Okay, it's like ping pong, but it's on a screen. It's one of the very beginning games. this is just a box to hold our display in, but it also has connections to 4 processors inside. So in principle, we could hook up 4 controllers to this and have 4 people playing Pong. So that was kind of my thought, 4-person Pong. I've never seen that before. We were hoping to do that, but we started out with 2. And now this brought up a really interesting question. We have an 8x8 array. Everything's homogeneous. All the processors do the same thing. And now we're going to come in and hook some kind of I/O device in there. What am I going to do? I've put some special code in the processor to handle that I/O device. But remember that virus scheme I had where everything got a copy of itself? Well, then that I/O code would be everywhere. We don't really want that. So the idea is that we will put the I/O processor in the box, and it pretends it's just another processor in the array. So that's how we handle that. So this the processor in this box, same as one of those, has its own special code. But when it talks to one of the processors in the array, it pretends like it's just part of the array. So that kept everything the same. So that box was designed and built by one of the students that worked with us. We had a lot of students working on these things. It's really interesting to look back and see how dedicated they were in making their contribution work. And I'll tell you more about one of those in a moment. So one student developed these, worked on this Pong game for the longest time. This shows you kind of steps we go through. First you think up all these ideas, then you make a prototype. That's what that white thing is. You plug everything into it, hook wires up, and see if it works. If it works okay, then you make a board. That's that little green thing at the bottom. We always have somebody else make them. Then we usually solder the pieces on. Have a box either made or purchased and card holes in it, and then put the board inside and get the finished product. So it takes a little while just to make a box. This is a carefully designed box with a button and a knob. That gives us 2 things, digital input and analog input. Okay, and with that, you can do a lot of things, including playing Pong. Well, let's move on. Another application, we're trying to make computers out of small things. These processors are small, but they're very complicated. So we have to think about things that are even simpler than normal processors. One of those simple things is called a cellular automaton. So we didn't build a cellular automaton machine, we emulated one using these processors. So that was another application. This is just showing, we had to think of a way, the way cellular automata work is they take information from neighboring cells, pull it in, and update their state, and send their information back out. So it's this exchange of information back and forth between the cells that had to be back and forth between the processors. So we had to work out a scheme to do that. So that's what that's representing. And then I showed a demo, and that was the cellular automaton running. And we used, you remember that? You could turn this little knob and we go faster or slower. Learned a lot from doing things like that. Okay, we had a group of students. Over the years, I've sponsored 4 computer science capstone teams who worked on different projects, and one year they used this to do graphics. And the idea is, remember, all the code's the same, so how do you get to draw something specific? Well, the idea was that you'd send in descriptions of 4 lines, and those 4 lines would define an area, and the processors would determine whether or not their pixels are in that area or not, and turn them on. That was the idea. So you just broadcast messages out saying, oh, I got these 4 lines, please turn on all the pixels that are inside these boundaries. And they did it, and it worked. They had a lot of fun doing it too. Oh, really neat thing about that, though, was we only had one of these, but we had quite a few of these, and so I turned the students loose and gave them one of these little 2x2s. They wrote their code to run on here, and then ran it on here with no changes. So that's important. It just shows that with a machine like this, you can write software that will run on any size machine. You don't have to rewrite the code or anything like that. It works. Okay, I'm going to spend a few of my very precious minutes on this issue. This is really key, I think. When you think about our brains, and I have this thing called observation here, natural neural systems, brains, things like that. are well known for their amazing capabilities despite the relatively low speed of their components, right? We know that. So how about if we could make computers that way? What if we had a lot of pieces that weren't all that fast? Could we get them to work and do something interesting? So that's kind of the hypothesis. Maybe we could make a computer that used a lot of small parts. That's kind of the thesis of this whole thing, that would do something like a brain would do. Well, why do we need that? We've already got computers, right, to program to do whatever we want them to do, and that's the truth. There's nothing you can't do with one computer you couldn't do with another unless you just run out of memory or something. Unless speed is important, right, or maybe power. So if speed or power are important, maybe you don't want to run it on a computer that uses a lot of power and doesn't run very fast. And brain-like processing, if you think about it, isn't very much like computers today at all. And so it's not unreasonable to assume, which I am assuming, is that if we try to do brain-like things on conventional computers, it's not going to run very fast and take a lot of power. Well, then what's the alternative? Let's pursue something. Now, as an early foray into this issue, I turned to neural net literature, got a big book, and looked for something we could do with neural nets. It came up with this thing called a self-organizing map. Self-organizing map. I thought, oh, okay, let's do a self-organizing map, because the idea of a self-organizing map is you start putting information into an array like this, and it locates itself in such a way you form a pattern of some kind where basically similar things are near each other and dissimilar things are far apart. Well, there's been about 10,000 papers written on self-organizing maps. 10,000 papers. Okay. So you say, all right, let's do it. Self-organizing map. So we did an experiment, we implemented it on this thing, and we discovered something, which wouldn't have taken very long to discover if we thought about it. You need global operations. The way that the algorithm works is if you have a bunch of data in an array, and you bring new data in, you want the new data to be located near the data that it matches most closely. How do you determine the closest match in an array of data? You have to search through and find it. That's a global operation. Global operations are not good because it uses a lot of power and takes a lot of time, which are two things you don't want to do, right? But I will say that having 64 processors doing it does speed things up a bit. So it worked, but this global need kind of bothers me. So we had to think of some other way that one could do things like this, and that's something I don't have much to show on because it's still futuristic, but it's the idea of clustering, where information moves but doesn't and changes location based on its local neighborhood. But it's not a global operation, it's a local operation. Okay, so clustering. And you think about the way our minds work, it's kind of like that. If I asked you to think of all the states that start with the letter M, did you think of Ohio? No, because things are clustered in such a way that you can quickly find the things that are related to the letter M. But probably not Ohio isn't in there. Right? There's just, I think there's something to that. Clustering is a nice operation for a machine like this, which uses local operations and a lot of parallelism. Okay, so I want to move on, but that was kind of the lesson of this exercise, is that if you just pick up stuff in the literature and start implementing it, they weren't really thinking about the type of computers that we are, and the algorithms are going to have to be a little different. Okay, on the reverse, this ability to sense light with LEDs, this is kind of a tangent. This isn't helping us get to the brain-like computers, but it's just an interesting fact that you can sense light with an LED, and we did some experiments to see how hard that would be to do. It looked pretty reasonable. I guess I won't go into how we did it, but it did work, and I showed you the demo of that. Okay. Now, since this program's predecessor was amorphous computing and paint-like computing, we didn't give up right away on the idea of having what I'm calling now autonomous nodes. Okay, if they're all together on a wallpaper, that's not autonomous. That's not what I mean. So autonomous would be like you take a bunch of tiddlywinks and just threw them on a table. That's kind of what this is a picture of. But you start thinking about autonomous nodes, what are some of the issues? I already mentioned them, really. Communication and power. Okay, how do you get power to a whole bunch of tiddlywinks on a table? How do you do that? There's been a lot of ideas, I'll say. But one that made sense to us was solar power, use light. Okay, we could use something else, but we picked light. We said, all right, we want to get light. But how much area do we need to power something like this? Well, if it's got LEDs on it, I'll tell you it's a lot, because LEDs take a lot of power. So I had this student, I'm really pleased with what she did. She got this is a flexible, fairly inexpensive solar panel. It's not the highest efficiency you can get. It's pretty cheap, 4 inches by 6 inches. And in principle, it should put out enough power to drive this little 2x2 array. So here's our experimental setup, a cafeteria type tray with the solar panel. Here's a little 2x2 and then some more electronics stuck on this prototyping board. What you do is you take this outside, sit for an hour in 92-degree heat and under direct sunlight and do experiments. And that's what the student did. That's what I appreciate so much. But she did that, and sure enough, it ran, just as we hoped. So, okay, that's fine, but this has 35 times the area of these 4 LEDs, this thing. So if I want this to be solar powered, I'm going to have to make it quite a bit bigger. And that may be okay. It may be okay. Another thought is, start playing these games. Well, maybe we don't need power all the time. We can have a battery. Sure, you can put a battery in, charge the battery, use the battery only when you need power, and so forth. So you start heading down that path, and there's been a lot of people working on that. We decided to table it. Let somebody else solve the problem. Although I had this thought, and I think a lot of people thought of this, but I don't know why I have to plug my cell phone in. Wouldn't it be better to lay it on a pad, just have it charge itself? Are you aware of commercial products that do that? Okay, so that would work. But how does a pad get its power? Well, one idea is it's a solar-powered pad, right? That would work. Another idea is that you put coils in it and you move your mouse around, you're charging it up. You could do that too. Or put a battery in your shoe as you walk around, you power the battery and you plug it in the pad. I don't know, there's all kinds of ideas. All right, here's another kind of wild idea. Since as long as we're working with arrays, and the idea was that if you have an array, you just attach some kind of I/O to it. Well, instead of LEDs and things like that, how about something tactile, something you can feel? Maybe we can make an array, then you put it on your skin somewhere, and you could use it for a couple of things. One application was some people don't want to wear prosthetic legs because they can't feel anything. Well, the idea is you put a patch there that gives you the feeling, some kind of feeling that's feedback from your prosthetic. And then there's this mental thing your mind does that sort of maps to that, and you can get feedback that way. Another idea is that you could use it to guide you through a room that you can't see, for example. Maybe you're blind, or maybe who knows what. So here's the prototype, just a helmet with a lot of electronics on top, and Dr. Lima's not here today. This was his project, and I was looking for a picture of him wearing this because it's hilarious, but it works. Basically, a battery-powered device, and in the front here, he's got sonar sensors, and then to give feedback, you have to do it some tactile way. So that's what the helmet is for. And inside the helmet, it's got a little strip that goes across your forehead with little motors on it, and it turns these little things back and forth, these little guys here. And he tried a lot of things. I mean, you could have things that poke at you and vibrate and shock you. And we were looking for something that didn't tear your skin off and drive you insane. So this is what he came up with, one of the ideas he had. There's a lot of ideas though, and it's an interesting project. There's a lot of science behind this because the skin is amazingly complicated. I had no idea until we started getting into this project how clever your body is. That's why your glasses don't bother you after a while, things like that. But how do you get past that to have this thing actually work? It's kind of an issue. Okay. Still on the concept of arrays of actuators or sensors or something, we had another idea. We've been outputting light, outputting vibrations. Now let's think about inputting vibrations in the form of microphones. Nice transition there, right? Anyway, so if we had an array of microphones, we could have an array of processors processing those microphones, and we know we can do clever things with microphones. If we have arrays of them, we can locate where sounds are coming from. But we wanted to get a feel for how hard that was to do, and so we decided we would give it a try and include that as part of one of our prototypes. So again, go through on this process of designing circuits and prototyping them, having these green boards made by somebody, putting the parts on, testing it, cycle that a few times. This is a board with 4 microphones on it, and I couldn't find a prototype anymore, but it's about this wide. Then a box was made for it, and then also we had to hook this array to the PC somehow, so we developed a node here that takes care of that, called interface node. There they are, pictures of them. And these can be daisy chained together. You can put a bunch of arrays together. You can see here that these 4 microphones, they're a fixed distance apart. But if you have 2 sets of these, you can move them around and experiment with different distances and things. So that's what we made that for. And these little teeny processors have ADD converters in them, so we could sample the microphones, convert that into a digital form. But the digital form are these little dots. Those little dots don't look like the waveform, so mathematically we fitted this waveform to those dots. And what we're interested in is capturing a waveform like this from each of a number of microphones. Each microphone is at a different distance from the sound source, so these waveforms should be shifted in time relative to each other by a very tiny amount. We need some way to detect that. So this data would be captured by the array, passed up to a PC. The PC would do this interpolation. Then there's an algorithm here. I won't go into explaining. This picture would help me explain if I took the time to do it. But basically it finds what that phase shift is. And so we did some experiments just using one array. And this is data from those experiments. And basically these lines are supposed to be pointing at the sound source. Okay, the sound source is represented by this little dot. And they're kind of pointing in that general direction. We're not pointing right at it, right? What we did here is we got 4 microphones. There's 1, 2, 3, 4, and we took them in pairs, different pairs, and compared the 2 pairs to figure out where it would seem to locate the sound. And that's where you get all these lines. Now, if you move that sound to the right, they all start pointing to the right. So it works, but they're sort of, that's kind of over there, you know. And why is that? We still don't know, but my latest theory is that if you go back to this picture here, those 4 microphones are on the same piece of material. Maybe as the sound hits one, it travels down the board, it's picked up by the other one. I don't know. So it seems like it throws it off. But if you take 2 of those boards, separate them, you get this case on the right, actually, where it's definitely pointing at where the sound is coming from. So it works when you have the microphones on separate boards, but not if they're on the same board. So that's why I think it's probably something like what I just said. So we're pretty happy about that. We actually got some decent results out of it. All right, now back to wallpaper computers. I told you we did all of these, and then there was this one. Now what happened was I went to the psychology department one day and was showing them this, and I noticed that when it was running, I couldn't get the professor's attention. He was just watching it. So one of the things we called it was the mesmerizer, because that's what it would do. In fact, we had a little one. This little guy took him to a conference, put it on the table. People come by to pick up brochures, and they get mesmerized again. So that's why it's called the mesmerizer. But what he noticed about it was that we had all these LEDs really close together, and they're colored as well. And he's doing experiments where he had an LCD screen with LEDs behind it. And the idea was that the LEDs could illuminate different parts of the screen and leave other parts dark. So, you know, if you want to make part of your image bright, you turn up the brightness on your display, but the whole thing washes out. But if you could have LEDs just behind certain parts and turn them on really bright, you could get some really high contrasts. He's doing experiments with that, but the LEDs that he had were all white and spaced far apart. So he wondered, well, could you put that array behind an LCD panel? Then we'd have a lot of resolution. We could do some good experiments with that. Well, I said, okay, let's do that, but you're going to need a little bit bigger array than this. And when we put it behind an LCD panel, we noticed that the panel wasn't passing a high percentage of the light. We'd like more brightness. So we want something brighter and bigger. So we undertook the task of making something brighter and bigger, and that's what led to this. We call it the acoustic imager because we attached the microphone array to it, so that in principle you could sit in front of this display, and if you talked, it would know where your mouth was, and it could maybe display a pair of eyeballs looking where your mouth is. But it could do other things, and you could actually use it for finding where sounds are coming from, like under your car hood. What if we had an array of microphones under the hood of your car? Every time some weird sound comes, it would locate where the sound was, and you want to see where that is, it could display an image of it. Well, this is like a portable device for doing that. The idea is you walk around, it's got microphones on it, and it shows you the sounds that it's seeing. So it's a combination of a display and microphones. We call it the acoustic imager. So now you can go to your car, you know, and point around in there and see things. Now, if you have an LCD panel there, you can overlay an actual image in detail of what it is you're looking at. So you could take a camera, display the output of the camera on the LCD, then in the LEDs you could display where the sound is coming from, kind of overlay it. Anyway, there's different ways of packaging this, but the technologies were basically the wallpaper display and then the microphone array. So we started out without the microphones, just trying to come up with something you put behind an LCD panel that would give you this high contrast. And then we had to think of a way to make it, and using strips again, but here the strips were flexible. If I'm going to put this behind an LCD panel, I would like it to be very flat and rigid, actually. So we had to think of another way to make it. These are a couple ideas, but they're not the ones we ended up using. We ended up making strips, and I'll show you the strips, and you'll see how they go together. Also, I said we had to have more power, more brightness, right? That meant putting more current through the LEDs. The current was going through these microcontrollers. They can only handle so much, so a big challenge was how do you get more current without burning up the processors? So the idea was, here's the original idea, oops, the original one on the top. That's Charlie plexing I showed you before. You see only one power connection here along the top that goes to the processor, and then it goes to ground. So all the current runs in here through the LEDs in the back here. So everything's running through the processor. Here's a different scheme. Here the current runs this way through the LEDs, then the processor, then the ground. So the current only runs through the processor once, not twice. Here it goes in through the LED and back through again. So it went through twice, right? Here it just goes through the LED and then down once. So we can have twice as much current that way. And the other thing we did is, instead of Charlie plexing, there's a different scheme where we can turn on 8 LEDs at one time. So, just to give you a feel, one LED draws 20 milliamps, 8 LEDs 160 milliamps. 6 times that is an amp. An amp's a pretty big number. We have 96 processors doing this. That's 16 amps. It's a lot of power. Thankfully, most of that is going to be light, but it's a fairly potent device when it comes to power. So here's the idea. We combine this bright backlight with a pair of microphone arrays. There's one on each side here, left and right. We call that an acoustic imager. This will have 8 microphones then. We've got 8 I/O processors. Remember I said when we do I/O, we put in a separate processor like you did with this box. Well, here we did the same thing. We had a separate set of processors to handle the microphones. Then there's processors in the middle that handle the display. As 96 of them. Each of them has 16 LED packages with 3 LEDs each. So you figure it out, it's 4,600 LEDs to make this display. And I mentioned it's quite a bit of power. Comes out to be about 60 watts. That's a lot when you're dealing with little electronic things. Now I want to give some credit now to the software. There's just so much software that went into this thing. And just to give you some feel, there's software in the PC that handles all this microphone stuff, downloads things, and gives you control of the processor, the device. That had to be written. Then there's that little node at the top that connects to the PC. That had to be designed and code written for that. And that includes a USB link, which is a protocol that's fairly sophisticated. Then each one of these processors on the edge that handles the microphones has a lot of unique responsibilities, including downloading code initially. So you wrote code for that. And then inside, you've got all these image processors, 96 of them. They all have identical code, but they handle a lot of things as well, including passing copies of their own code to other processors, communicating with each other, displaying the LEDs. And if you're sensing light, they have to do that task as well. So there's a number of things to be done. And the latest version of that code, if it's printed out, is about that thick of just code. That's a lot of code. So here, hardware-wise, this is one of those strips. It still has, the actual strip is just from here to here. This is for handling. This is kind of an artistic picture. But what we did was, there's 2 rows of processors on each strip. To cover this whole area, we figured we need 4 such strips. So here's one of those strips being tested. Now you're seeing the other side of the strip where all the LEDs are. So this design puts the LEDs and the processors that control them together on the same strip. But we connected them to each other. Now how do we do that? Well, there's another strip actually. It runs right down the middle between these two. It's very thin and uses the exact same technique that we used to make this, where you have little teeny holes, solder filling those holes. You apply some heat to those, and then they make connections down below. So these boards, these little strips here are actual boards. They're just a very thin version. Has no electronics on it other than wires that connect from one side to the other. And that worked out really nice, I think. And it looks good too. So that's how we put them all together. There, it actually works. Now, this picture, we've got a YouTube video of it you could see, but every one of those LEDs is controlled by a separate processor. So you're seeing 96 LEDs under control of 96 processors. So we could do a lot of high-speed stuff if we wanted. And in fact, 3D displays would be a very logical next step. With all this processing power, we could handle what we need to do to make 3D displays. Now, that's just the display. This display serves as a backlight unit. So the backlight for a commercial device was removed. So what I have here, this big box, between my 2 hands, just holds the electronics for the LCD and the little connector board that we needed. Our board is over here, which is mounted directly behind the LCD panel, serving the purpose of what was originally just a fluorescent backlight. So it's interesting that we were able to design something that's flat enough to slip inside of the device that wasn't designed for it. But we did that using low-profile parts. I put a temperature sensor on every one of those processors, just in case. And since everything under software control, if it gets too hot, you can just turn the LEDs off. So that's a nice feature about this. All right, now we're going to use the last part of this talk. Just how many minutes I got? Can't read things glare. 15? This is starting to head down more seriously the path that we started out on, which is making things out of very small parts. So far, the parts that are small are off-the-shelf parts. But let's say we have the freedom to make whatever we want. What should we do? Well, we decided we were going to go with available technologies. We'll use integrated circuits. But we need to think of a small part that you could make computers out of. What would that be? Today, computers are usually made out of processors. That is not small. There are many thousands, many millions sometimes of transistors in one processor. We wanted something smaller. What could that small thing be? We started out with something that was clocked. Most computers do have clocks. We decided we would have a clock too. We designed a very simple little thing called cell. This cell is like a one instruction. And what this instruction does is combine 2 bits. You load the instruction into this cell, into this blue area here called shift registers. That's what's holding the instruction. Then you feed it the data you want to process on, which would be 2 inputs that come from neighboring cells. It combines those 2 inputs and produces an output. This is the core part that actually takes the two pieces of data and combines them into one. So it's a 1-bit processor. It takes 2 bits in, produces a bit out. But what it does is determined by what's stored in this part of the cell. And that can be changed. So it's a programmable cell. Okay? We call it a Boolean cell because it just works with a single bit. It's small, only 40 microns on the side. That's pretty small. But it is clocked. And we looked at things like that. You know, how do you distribute the clock to all its cells? And what if you have something as big as a wall? You have to distribute this clock over the whole wall. People are having trouble distributing clocks on chips because they're so fast. How are you going to do it on a wall? Well, it can be done, but it takes a lot of overhead. And the worst thing about it, though, and Dr. Yu pointed it out, is that if you're clocking all these cells, they're all going to be dissipating power all the time. This thing's going to get very hot. The only reason most chips don't burn up is because most electronics on the chip is not being used, not at the same time. But if we clocked all these cells, we would definitely melt the chip. So how do you solve that problem? Well, you go asynchronous, right? The idea here now is that you don't have a clock. You let something else determine whether or not the cell is going to compute. In this case, the first idea was just a signal we call the trigger. And a trigger, just an impetus electronic pulse that comes in. These represent cells. So here's like one cell that's triggering the next cell to do something. So if you're not triggered, you don't do anything. So everything's triggered. These electronic triggers cause things to happen. Here's an example where one cell triggers 2 cells. So that's how you can get, besides nuclear fission, you can get mass parallelism by having them trigger more than one. Then you have the reverse case. This is called a fork. This is called a joint. We're bringing 2 things together. So we had designed cells that would work this way. Some kind of a trigger would do an operation, be able to split things out, join things together, and also you need to be able to turn, left and right. You have to steer these triggers around in order to do what you want the computation to do. And keep in mind, these all have to be programmed somehow. So we designed a new cell called the triggered cell, or T cell. And here's a quick view of it, it's just, here's the little processor, here's where the 2 bits are coming from, this is the output. You start with that. That has to be triggered somehow. So here's the little, this is the path for the trigger to take. So the idea is that trigger comes in here, it causes something to be stored here, then this sends out a new trigger that stores something here. But notice I have 2 paths. I have a path for the data here, a path for the trigger there. Now you can string these together. Here's 2 cells strung together. We still have the 2 paths. The 2 paths are a problem because the trigger path has to be slower than the data path. You have to let the data get there first. So you have to think of what's the worst possible condition and make sure that that's not going to cause a problem. What ends up happening then is that you have to design for worst case. You'd rather not do that. You might not even know what the worst case is. But if you do know, you design for it, you're sort of guaranteed to run as slow as it would ever run. It takes care of the power problem, but it kind of is a speed issue here that we'd like to get away from. Okay, so we came up with a new design, and this one we liked, and we decided that we would actually make a chip using this design. So a lot more effort went into this one. Instead of a trigger, though, the idea was that we would have, I have a slide for it. We would have only 1 pulse, not 2, not a data pulse and a trigger pulse, but 1 pulse. Now, how can you tell from 1 pulse whether it's a 0 or a 1? Well, you color them. Use green ones and no, you don't color them. But you put the pulse on a separate wire. If it's on one wire, it's a 1. If it's on the other wire, it's a 0. Okay? So you don't need a trigger anymore. The data itself is the trigger. Now you get away from this issue where you have 2 things running in parallel and have to make one slower than the other. Okay? So that's the idea. So you have a pulse design. Instead, everything works off single data pulses. So if you're going to make a real chip, we have to make all the details, work out the design. We started out with schematics. And this is just a high-level schematic of a cell. Now in this case, it's a quad cell. It actually has 4 cells together that are put together into a quad. The reason we did that was that way each cell can have an orientation, left to right, right to left, top to bottom, bottom to top. Everyone has his own instruction, so the instruction that this cell performs depends upon which direction the data comes from. It was one of 4 things. And then there's a little bit of shared circuitry in the middle that we introduced for synchronization. So that's the design. So it's a quad cell. Each one of these things here, that's a small single cell. We call it a quarter because it's a quarter of the cell. Here's what a quarter looks like, and it's sort of like what you've seen before. There's an input unit, selects where the data is coming from. Here's the unit that processes it, and then here's the output. Now we add a couple more things. This is where the instruction resides. It's a default version and one that you supply. And this is the piece that connects to that middle that's used for synchronization. So it's just a basic idea. It's like a little computer all of its own. You put 4 of these little teeny nano processors in one quad cell, and that's your building block. And it's asynchronous, so there's no clock. And power is not an issue anymore because we're just waiting for computation to take place. There's no power used. And it can be any size because there's no clock. So if you're going to make an actual chip, you have to be very careful because you're only going to get a few chances at it. In our case, we had 1 chance. And so we did some simulations early on using the schematics. Then we started laying out the chip itself. But first we automatically generated these. These are actual quad cells that have been laid out by a tool. And then we would glue them together to make this array. It's a 7x7 array. And in addition to the cells, which are in the middle here, this 7x7, there's some little I/O blocks you can hardly see that allow us to connect these chips to each other. So you can put a bunch of them together and they all talk to each other without any glue in between them. And so that's what these little things are. They're the I/O devices that are inside of this chip. After you've got the layout, now you have more information about the transistors and so forth. You can do a more detailed simulation. They're much more time consuming. We don't have much compute power here available for that, so we were very careful to simulate only a few cells at a time. And that's what this is an example of, is 3 cells, and we're testing some communication between them to see if this thing's going to work or not. Well, here's what we got back. This is 4 chips actually on one die. We did that because our contract was to make 100, but we only had enough money to buy 40. So we designed them so we could saw them into fourths, so we'd have 160 when we make the contract. So instead of making a big array on the die, we made 4 little arrays, and then we cut these into pieces, so that was one packageable part then. That we packaged ourselves, which was quite a challenge. Loading involved, no. And then we started testing. Now, testing is quite interesting because the chip's just sitting there. How do you test the chip? So we had designed something that would hold the chip and give us access to all of its pins. And we had to find ways to load those bits in there. Remember I mentioned there's instructions. Well, there's 6 bytes of data per cell, and we have almost 50 cells. So we're looking at 300 bytes of bits. You don't want to come up with those bits manually. It'll take a lot of work. So we wrote a simulator that would allow us to design patterns like these. These are patterns. This is 3 cells working together. There's 3 more, 3 more. This is a pipeline. This is an oscillator, another oscillator. We had to design these things and somehow create the bit patterns that would, if you load them into the chip, would perform this function. So this is just showing that board I just showed you. Here's the simulator. This was another, I had 2 computer science teams work on this, and then I ended up working on it for about a year after they did to get it to where we were. This is our cell array, 7 by 7, and each one of these is a quarter, as a cell, divided into 4 pieces. Each one of those pieces is a quarter. So it puts up a display, allows me to specify what the instruction is in that quarter. And then I can go through and load them all up. Then this thing would spit out the bits, and we would load it into PC and send it down through into our test set, and then see if it worked. So here's the code written on the PC for reading that. Here's the test bench. The thing I want you to notice is the chip. You see the chip? There's a big pile of wires here, and underneath that big pile of wires is this board. And in the middle of this board is a little connector, and you open that up, find the package. Inside the package, you find the chip. So that was kind of interesting. One of the big problems we had is that connections were always not connected somewhere. Something wasn't connected. It's hard to figure it out. The chip actually worked, which is quite interesting. It didn't work completely, but we could program it, and we could get it to do things, and it ran very fast. The pipeline itself, we made a pipeline. A pipeline is where you're sending bits down a path, but you don't want the bits to catch up with each other. So you need some kind of feedback to make sure that they're spaced evenly. So it's not the maximum speed you can move information through, but it's the maximum speed without anything bumping into anything. And that would run at 1 gigahertz. That means you could get through 1 cell in a nanosecond. So it didn't take very long to get through our array at that speed. But that's the speed of a pipeline in this design. Those oscillators that I showed earlier, they run at about 500 megahertz. And they're not optimized for speed. Just show you how fast it goes. Here's the actual chip. I showed this to one person. They asked me, why did you make your chip look like a quarter? But it's not the quarter you're supposed to notice. It's this little square here. I just want you to see how big the chip is. It's not a big chip. It's a very small chip. The technology we're using is 6 generations behind the state of the art. So it could be a lot smaller than you see. And we haven't tuned it for speed or anything yet. This is our first cut. Okay, we've got a patent on this chip design to look into it. We've published a paper describing it. But we're not done. Now we've got a chip, but people are going to need to program this chip, and they need to know what it can do. So we started working on ways to program the chip, and we had to have a way to explain to people what the chip does. So we came up with this very simple picture of a cell right there. So if you're a programmer, this is how you would think of this cell. And you put these 4 cells together to make a quad cell. So you can just focus on each one of those. But what if you don't want to pay attention to the fact that they're stuck into an array? Maybe you just want to design things freely, using your artistic flair, and then have some program jam it all in. Well, that's certainly allowable. So in that case, came up with a different representation for the cell. I made it, it's very small, and that's the point of it, because if you make something big, complicated, it can involve a lot of cells. So we need a way to make them small, so you put a lot of them on the page at once. You'd probably make them in hierarchical groups, so you don't have to see all the detail all the time. But here's an example of a gate made out of 3 cells, self-synchronized. So you can send data into it in any order, it will always work. And here is an adder using each one of these squares would be a quad cell, and it's showing the cells are actually using this adder. This is an asynchronous adder. So we'll add 2 bits and a carry bit and produce a result and a carry out. And what we'd like to do is just keep putting these things together, make multipliers, and start showing people how this chip would do digital signal processing, things like that. What is next? That's the end of my talk. So I've got the things here. You can take a closer look and see what we've done. We've got a lot of ideas what could be next, but we'll see. All right, so thanks for coming.